Okay. So good afternoon, everyone. Welcome to our talk. And today we are going to talk about the JIT-Embedding service we build using Reserve, and then how we use it to power large-scale multimodal foundation model training in Adobe Firefly. It's the quick introduction of ourselves. I'm Haoran, and my colleague Baqiao is here. Both of us are working in Adobe Firefly AI platform organization. In our organization, we are building AI platform all the way from data to training to inference, and powering Adobe Firefly first-party model, as well as supporting deep tuning for our enterprise customers. So in the next few slides, I will introduce some of the products we are helping shaping and building in Adobe Firefly. So last week in our Adobe Max conference, we announced the Adobe Firefly Foundry service. So Adobe Firefly Foundry provides our enterprise customers with private and deeply tuned AI models across image, video, 3D, audio, and vector. And both me and Baqiao were the founding team members for Adobe Firefly Foundry and help bootstrap this effort from the grounding up. On the image side, we released our latest generation of the Firefly Image 5 model. So this model can natively generate visually stunning 4-megapixel images, and particularly good at generating photorealistic details. For the first time, we were also releasing our first audio model, Generate Soundtrack. So Generate Soundtrack enable our creators to generate original studio quality instrumental music that are tailored specific to our video content. Last but not least, last quarter, we released the updated version of our Firefly video model. In this updated version, it improves our motion quality and also provides our users precise video control in their workflow. As always, for our Adobe Firefly first-party models, we trained this model responsibly, and also all the models from Adobe Firefly are commercial safe. So next, we'll talk about the background for this JIT-Embedding service. As we all know, all the way from latent diffusion model to diffusion transformer DIT these days, embedding is the universal interface that make multimodal generation model work. So it's very important to run embedding efficiently in our training workflow. High-level speaking, there are two ways to generate embeddings. On the left-hand side, we can, of course, generate embeddings on the fly. It will provide the maximum flexibilities. However, it's not the most efficient way to do, because during the model training process, computing VAE embeddings is going to consume our very valuable GPUs, both GPU memories and also the training time, because we want to spend more time on the forward and backward instead of on the frozen model. Of course, on the right-hand side, we can use our favorite data processing framework, for example, Ray and Ray Data, for offline embedding pre-compute. From the training perspective, it's the most efficient way, because during the training, the data loader is just going to stream pre-computed embeddings from our cloud storage on the fly. In reality, during the training phase, large-scale foundation model training phase, our VAE changes most of the time, several times during this training period. And every time when VAE changes, the underlying embeddings also needs to change. So it's infeasible to pre-compute every version of the VAE embeddings for all the training data we need during this pre-training phase. So at the end, in order to make us competitive in this fast-moving GenAI field, we need to move fast. And we need to find a balance between flexibility, speed, and also cost. So now I will pass this to my colleague Baqiao, who will talk about how we find a balance using JIT-Embedding service and reserve. Thank you.
Okay, so it's kind of clear what we sort of want to do here. So sort of as Haoran already introduced, the problem was that we have a lot of flexibility needed. VEs change version a lot, their schema changes a lot, the data shape changes a lot, the underlying latent space, the manifold changes a lot. And at the same time, if it changes so much, we don't want our training machines to spend so many cycles just to recompute them over and over again. These are expensive machines. These are small models. It never really makes sense. For example, these are H200s. You run really small scale models. It's just a waste of money, especially given the limited resources we have. So there's all the idea machine learning is basically called a feature service. So we have this idea where we just essentially adapt that, and we call that just-in-time embedding compute. You can tell that we weren't the most compiler-minded people back then, but still. It's called just-in-time service, in which you simply delegate the embedding compute to a dedicated service, and then the training machine can just asynchronously retrieve such embeddings. The high-level design is sort of obvious, so just to go over it. I mean, there are many frameworks we can choose. We chose Razor for its specific flexibility on the server side. It's the computation. Everything can be stateless. And in the end, if we need to do it again, for example, if we run a training for multiple epochs, there's a chance that we can do async materialization. Client side, we, just like everybody else, uses PyTorch. So in this case, we just integrate it with Torch data loader and with a bunch of prefetch. More interesting components can be set. For example, there is a Rust-based serialization and deserialization framework that we use extensively in this project. So I mean, the high-level design speaks for itself. The devil is really high in the lower levels. But given that we have a bunch of training jobs and there's already a data loading component for it, for this unfamiliar data loading is the sort of sophisticated, usually somewhat low-level engineering of how do we keep the GPUs fed. There's tons of bytes that they consume. There's tons of augmentation that they do. So data loading is a part that does that. And so we just integrate that with our external service here. Some interesting design choices that we deliberately made for this project was that, for example, the data loading client, the JIT client, sends directly the media to the service. And then the service, given that it's running VEs or other types of models, it also generalizes, directly returns the embedded tensor back to the data loader component. Data loading extensively makes use of prefetch because, or else like, it's kind of like fetching things from high latency storage, such as S3, can sometimes have high variance. So usually prefetch, and also for other reasons, is used to amortize the cost. So here it's also used to amortize the cost of running the VE service. I'm going to talk more about it later. But again, the high-level design here is definitely simple. I'm not going to get a promo for this, for doing the high-level design, but the devil lies in the details. So like, we schedule design, we implement it. Like, Reserve is very easy to use, data loading components. You just wrap your stereotypical HTTP client, and then you just send requests to Reserve. So how, like, why are we talking about it here? So there's more to it. In production training, given how fast we move, given the fact that there's inevitably going to be periods where people, like, the training job dies during the weekends, that everybody has to be waking up. Things can go wrong. I mean, who could have guessed? We all know the Haoran days are training foundational models. So there are several things that have gone wrong, and that make that sort of design more interesting. So let me briefly go over them. So I want us to do this more as almost semi-interactive exercise. So recall in the high-level design that we directly just send media to the service. The one reason we do this, as opposed to, for example, just an asset ID, was that it's just due to a lot of technical choices. Our data loading component, for diversity of data, for various reasons, does a lot of augmentations on the data. So it's much easier to just send the entire augmented data to the service and then have the service send things back. Now the problem is that, okay, then how do you send images, videos, audio to the server? Kind of has for 5 seconds, and so the solution is sort of easy in that it's playfully obvious that you just want to encode the image, video, audio some way, like there's standard codecs, images, PNG, videos, etc. The problem with that is that you don't want to just blindly call these codecs. You want to choose the most efficient codec. It's what you send over the wire problem all over again, sort of. So in the end, we wanted things to be fast. And, like these things are running on the server, on the client. They need to match because we need to use the same codec. There's a lot of low-level bindings to C and also other Rust libraries. It is, to our knowledge at the time, that the fastest JPEG decoding library was written in Rust. So we just chose to implement everything in Rust in the serialization, deserialization framework. In addition, we carefully did choose, thanks to also expertise inside Adobe for working with media for such a long time, the best codec for each modality. We don't care about compression artifacts that much. We just use JPEG and these sort of things. Sort of videos, we just directly use H.264 because we do have a lot of expertise working with it. Audio, we also use suitable things such as MP3 or WAV, depending on what type of fidelity we need. And in the end, there's a lot of low-level optimization. The server and the client, they all run limited number of CPUs. And part of what we want to do is that we want to save costs in the first place. We don't want the training machines to spend so fast just computing embeddings, so that we don't want the overhead to be so large. So in the end, it's, again, a lot of low-level optimizations, zero-copy deserialization, vectorization, these sort of things. Now, the second problem here is that if you sort of play with stable diffusion before, the variational autoencoders, the VEs, they can sometimes have high latency, especially if you want high reconstruction quality. That's the reason why sometimes you have distils of stable diffusion VEs because they will run faster. But we are looking for quality in the pre-training phase. So right now, the problem is that we're not exactly running your typical crossover. In the end, everything is exposed to a REST-like API. But in the end, we are not doing CRUD. Thank God we're not doing CRUD, but that means that when you run the VAEs, things are super high latency. If you send a request now, like depending on the model workload, depending on how occupied the servers are, you might only receive it a couple of seconds later if the server is very congested. So in such cases, the problem is that the model cannot wait for 70 seconds, right? Like the model asks for a batch, you send it off, the request, you wait for a couple of seconds, then what's the GPU doing? It's doing nothing. It's wasting money, and we are not going to be happy with that. So a nice thing about our internal infrastructure is that remember, we're training on hundreds, at least, of GPUs. Each generation, we do have a batch that's being fed to each individual GPU so that we spend them as much as possible. But our internal infra allows us to have a so-called thing called order determinism. It means that we know beforehand precisely what's the order of the data points, at least to some optimistic degree. Like distributed system is hard. We cannot guarantee that the data point is even available via our object store, but in the end, we do have order determinism. That means that we have an oracle that can directly tell us which data point we're going to load. So that makes things easy. We can do just massive prefetch. It's sort of like pre-ordering for a party. Like, if I have a party right now, I'm not going to order my pizza right now. Without just buying for trouble. I will order my pizza at least an hour before the party actually starts. And also, given that we're serving so many GPUs, the latency must be hidden via massive concurrency. So the general thing here is that we are just doing this high-level planning to ensure that everything's orchestrated, so training never starves. Sort of, as I will later mention, all of the goal here is, as Haoran probably also hinted, that we really want our training GPUs to just do one thing, forward, backward. Anything else probably is a waste of time. And just as I wait to the next thing, in the end, some of the latency is caused just by imbalanced workload. And for example, if you're doing multimodality, it's sort of hard for us to, like, some servers might just be inherently more busy than the others. So we did something that we call client-side load balancing, which is related to this challenge. So sort of it's inevitable, right? You're running different models. We want to run it on heterogeneous hardware. In the end, it's about saving costs. So we want to, so instead of like training, I'll run on H100 or H200s. We get our hands on whatever GPU we can get hands on. And our payload is also heterogeneous. It's different kinds of media. The GPU is also heterogeneous. It's a heterogeneous cluster. So now our problem is that how do we deal with balancing? How do we keep also the JIT servers, the embedding servers occupied? So our solution here is we do specifically client-side load balancing. So it's basically you get the manifest of servers from the head node. The reason why we do this as opposed to server-side, there are two reasons. The first is that it's a straightforward way to avoid routing these large requests, for example, that are encoded media to the head node, for it to just relay again. That's a single bottleneck that we want to avoid. In addition to that, each client, they sort of know the best what they need. They know how far behind they are. They know like what type of media they need. So it's like, instead of it telling the head node to do what it can do, like this design allows us to later, for the client side, to enable their own profiles. And this will enable various types of load balancing strategies that gives us the freedom and flexibility, especially given our deadline at a time. So, and also, just sort of as I said, there will be no central bottleneck. So essentially, we are getting to this. Like, this is the money side. In the end, we are a business. We want to save money while delivering the best product for our customers. So in the end, like, before we did this, like the machine zero, which is a train machine, would just be like embedding. The for backward loop must be for embedding. And then the embedding part is never really occupied the GPUs that well in the first place, which is not good. And afterwards, it's just a form of pipeline parallelism almost, in which you just overlap the computations. And that's what optimization is all about, overlapping computations. I'm gonna lastly show some code here. So, like we said, a reason why we chose reserve is that it's very flexible to set up. Literally, there's an endpoint called encode. It takes a request, we deserialize the request, we encode it, we serialize the response, put it back. It's just as simple as that. Reserve is great. Sort of as a fun part or a flex here is that sort of as a hint that we do a lot of serializer and deserialization. One problem with serializer and deserializer is that usually you want to pair them together. And once you start to pair them together, it becomes less flexible or easy or error prone. So inspired by Haskell category theory and all that shit, what we did was that, so let's say this. So Adobe has been using sort of the principles of mathematics for inspired programming for a long time. So here, one talk classes here at Adobe about specifically how to do programming properly in our C++ code bases. The book is published by Semi-Group Press. So let us say this. So oftentimes in prod, we want to switch up the codecs because like we need to experiment. So let's say you serialization, you do LZ4, very cheap, and then you pack it for a wire. For example, you frame it with headers or something like that. Now, what do you do on the deserializer side? You sort of need to unpack it and then do the LZ4 decompression. The problem with these is that as soon as you change these a lot, you sort of have to change the client cycle, server cycle again and again, and so you're implicitly encoding this logic of the composition of two functions when you do the inverse of it, because these are actually isomorphisms. You have to switch the order up. It's kind of error prone. It's kind of decreases our efficiency. So inspired by optics and all that shit about what category theory isomorphisms, what we did was that we directly paired the functions together so that in our code base, LZ4 is an isomorphism between bytes. The packing of the request is also isomorphism between arbitrary byte payload to our request format. And you just directly compose them and you get a bidirectional function directly back without all the manual compositions. So we got auto array, like just to briefly mention, we got scalability, like reserve does scale. Like we scale to thousands of production-grade GPUs. It's very easy to deploy. Everybody understands it. We can't just add GPT about it. Everybody uses it. It also has a layer of built-in observability, which in production settings, we need observability, or who else are we going to consult at the middle of the night? So just for our conclusion, so this did power our foundation models that are in prod today. So in the end, after all these, what we got was that things iterate much faster, sometimes much faster. We save money, and also we did deploy a lot of VEs. They change a lot, and then we had to redeploy services a lot, spin up, tear down. Having something like reserve really helps because everybody knows sort of how to spin these up. And then we also enabled really these sort of high-res workloads where the VEs become expensive and become sort of the part that you need to optimize if you're optimizing for cost. Notable future work include the fact that, Ray, sorry, as announced, also mentioned today is that they actually have support for RDMA now. So when we send requests, we no longer have to go to HTTP. We sort of didn't have time to optimize for it. So now we can just use RDMA to directly to send a request. That was be a huge win. Thanks, Ray. In the end, ever since our first training of these foundational models, we are starting to have more use cases for different types of services, not just embedding. For example, VM is now used a lot for example, for instruction-based editing, these sort of things, and also for GRPO post-training. So it's a direction that we can explore, has good synergy with Ray. And also we can literally just send the compute graph over the network. We didn't have time to do that, so we had to send over the media. It's an opposite optimization we can do if we ever have time. And now I'll let my four managers talk about who we should thank.
Yeah, thanks. Thank you, Baqiao. I think for large changes like this in our large-scale foundation model training, it involves a lot of collaborations. As Baqiao mentioned, even though the idea is very simple, there is a lot of low-level optimizations, coordinations, collaborations around this change. I want to especially highlight Steven Feng in our team, who helped us with this project, as well as our close partner with foundation model team, Kai, as well as all the engineers and the leaderships in our AI platform organizations to help us push this forward for these big and ambitious changes. So lastly, Adobe Firefly is actively hiring. So right now we are hiring actually applied scientists across all levels to help us with our new Adobe Firefly Foundry efforts we mentioned about in the talk earlier. Thank you very much, and I think we are open for some Q&As. Yeah. Thank you.
Oh, sir, can you repeat that again?
Yeah, why we do serialization?
Yeah. Sorry.
So I think the question is that why we are doing serialization and deserialization.
Yeah, so the practical reason for that was that I would say serializer and deserializer, we can view it as somewhat more general. If you're sending bytes over the network, you usually don't just send the bytes, you reframe them somewhere. So yeah, let's view this from the higher perspective. But generally, it's we're sending signal over the network. They are just media. And it doesn't make sense for us to just send raw signals directly because there's always a chance for us to directly compress it and then decompress it. So I guess that's more of the serializer and deserializer part. It's just from a pure signal handling point of view, we want to compress them. So that forms the bulk of the serialization and deserialization. Hope that helps.
So in terms of your experience of deploying a Lego variation autoencoder separately and getting embeddings on the fly, if you would have to implement it, say without the rescale, how difficult would it have been, and how your flows were getting easier?
Wait, so you said the hypothetical scenario without deploying reserve, right? Like compared to
Like if you have to implement this on your own.
yeah. Do you want to take it? Or I can repeat the question.
Yeah, I think
yeah.
so. Earlier in the slides, we mentioned about some of the advantages we provided from reserve. Like I think one key thing is this built-in observabilities. I think that's very, very essential. Especially you can think of you scale up this large-scale foundation model training. At the same time, you have another fleet on computing embeddings on the fly, and they are kind of needs to play the throughput games in order to match each other, to not have bubbles and training spikes. So like during this large-scale foundation model training time, that those metrics, that observability that's provided by reserve is really essential for both on the platform side as well as on the training team side to understand the insights and to help debug if there is any issues. But do you want to add on anything?
Yeah, I guess. So I guess from a more personal point of view, it's essentially like I was on the front line, and if something goes wrong, I need to answer for it. And so specifically for reserve as a framework that's widely used, it's something that uses the underlying technology is record and also the exposure interfaces through a REST API. So in the end, like these sort of familiarity of the concepts helps frontline engineers like me to stay sane and to develop more features. I guess that's one part that I want to emphasize.
Go ahead, please.
The JIT server, if you had a parameter server, is that how you would implement it?
Sorry, can you repeat that again?
If you were to deploy a parameter server, would you use the JIT server as the layer to implement it?
Yeah. So I think the question, if I understand correctly, was essentially if we were to have a parameter server, is a JIT server also the way in which we have this parameter server. Let me think. So I'm gonna be honest, I never really worked with parameter servers, so but because how our model is like distributed as simply, I don't think we need a parameter server. But what I should say is that I mean probably not. That's because in the end, like parameter servers are particularly stateful, and we specifically designed the JIT servers to be statelessly scaled up. If something that's more stateful, I imagine that we want something that's slightly different in design. And also this is sort of heavily optimized for the fact that we are sending these sort of large media and tensors in and out, which is probably not the case for parameter servers if I have the expertise you would say so. Yeah, go ahead.
Yeah, I have one question. Since the JIT-Embedding service is also running on the GPU, right?
Yeah.
So what if you co-locate them in the sandbox? Maybe high-case on the GPU for data processing.
Yeah.
I know like calculators and diffusion for this, but theoretically you can do this, right? Is it because there's some balance issue about like the number of GPU you use for the loading of the data from the inside? It's not like the bottleneck like trends.
Yeah, well, I guess let me repeat the question. I've got as a part of it, and I think Haoran will be happy to answer the second part. So, so I think the question was essentially like, can we just co-locate the service with the training? Like in the end, like I don't know. Our goal is to simple overlap, so there is definitely a case that can be made that machine zero just does all the overlapping computation, right? So, so one part of it is definitely that we have spare GPUs. So we want to use them. These spare GPUs cannot run our foundation model training, so we're going to make use of the hardware. That's one part. But there's a bigger story that I think Haoran will be better equipped to answer.
Yeah, I think the bigger story is really just the cost perspective. Actually, during our development cycle, that we started to have this JIT local mode, which exactly does the things that you described, that we pre-partition some of the basically GPUs in the local node. Some GPUs doing JIT, some GPUs are doing the DIT model training. And later that when we want to scale it up, because at that phase of the foundation model training, we are mostly using H100 for DIT, and then for P4D and P4D nodes, those A100, A10G nodes, that we want to fully utilize that, and for the distributed VAE in computation. So that we develop this kind of strategy that we can fully utilize these two fleets, and we can scale it up independently, like kind of independently, like if we have a nodes, certain number of nodes for the DIT, and also depending on the training data as well as the VAE properties, that we can use that to guide our scaling properties on the lower end GPUs for JIT.
Yeah, have we considered that? Yes, we consider it. Essentially, thank God we now have more direct support from rate that will likely make our lives easier under the tight deadline. So if we were doing it now, maybe if it's under our deadline budget, and we would just do it. Yes.
We're very excited about this new feature which was announced today in the keynote.